Alright, so Gay-Lussac's law, after this would be your third formula once we get to it. And when what this says is when the Kelvin temperature of a gas is doubled at constant volume and amount of gas, the pressure also doubles. So let's look at a scenario where you have a cylinder of gas and it's at 200 K. Pressure is 1 atm. You raise the temperature to 400 Kelvin, and what would happen to the molecules? Once you raise the temperature, the molecules are going to acquire what? More kinetic energy, and they're going to move faster, and they're going to strike the walls of the container more often. The volume is being kept constant, so with the extra energy that they get, they're now going to be exerting more pressure on the surrounding walls, right? Which means temperature and pressure are directly proportional to each other. And this is the last online lab that you'll be doing. So Gay-Lussac's law states the pressure P of a gas is directly related to its temperature K when volume and number of moles are constant. Notice the number of particles here are the same, they haven't changed, so which means the number of moles are constant, because number of particles means number of moles. If the pressure increases, then the temperature K also increases. When the Kelvin temperature of a gas is doubled at constant volume and amount of gas, the pressure also doubles. And the relationship would be written like this, where pressure 1 over temperature 1 equals to pressure 2 over temperature 2, with no change in the number of moles and volume. And all temperatures used in gas law calculations must be converted to Kelvin. And we already know this because we did this for Charles's law, where we had volume 1 over temperature 1. We changed all Celsius temperatures to Kelvin. And you can rearrange the equation. If you want to get P2, for example, you would multiply both sides by T2, because you're trying to isolate the P2 variable, and you would end up with this. And also, you know that you can plug in the numbers and then isolate whichever variable you want to also. So a gas has a pressure of 2 atms at 18 degrees Celsius. What is the new pressure when the temperature is 62 degrees Celsius? All right, so let's go ahead and work this one out on the overhead. If you all want to go ahead and copy the problem quickly, and then we can, or do you want to try it yourself? And let me keep the problem up. Since you know the formula, pressure 1 over temperature 1 equals to pressure 2 over temperature 2. And pressure 1 would be 2 atmospheres, temperature 1 would be 18 degrees Celsius plus 273. And then temperature 2 would be 62 degrees Celsius plus 273. And you're solving for P2. Do you want me to work this one out, or do you want to try it yourself first? All right, go ahead and give yourself a minute, and then I'll work it out. You can, yeah, you can. First, make sure your variables are plugged in the right places in the formula, and then you can cross multiply. $18 degrees Celsius plus 273 will give you 291 K. Pressure 2 you're trying to find, and T2 would be 273 plus 62. That's 335 K. So this is how you would set it up to start with. You start with this, and then you can cross multiply, and you get P2 times 291K is equal to 2 ATMs times 335K. And then you divide both sides by 291K. Kelvin and Kelvin cancel out. This and this cancel. So 2 times 335 divided by 291. You should get 2.3 ATMs for the answer. Any questions on this? You could have, if you were trying to solve for P2, you could also have rearranged the equation here where you would multiply both sides by T2. Oh. This and this would cancel out, and then P2 would equal to T2, that right there, times P1 divided by T1. So you could have had it, you could have done it this way too, instead of cross multiplying. Any questions? No questions? Okay. Let's go back to the PowerPoint. I'll go ahead and use the gas laws to complete with increases or decreases. Pressure blank when temperature decreases. What happens to pressure when temperature decreases? Pressure also decreases because pressure and temperature are directly proportional. And then when temperature decreases, pressure, what happens to pressure? Decreases also. Pressure blank when temperature changes from 12 liters to 24 liters. Temperature is increasing, so pressure would also increase. Pressure blank when temperature changes from 45 to 15 degrees Celsius. Pressure decreases also because, once again, pressure and temperature are directly proportional. All right, here's another one. Can you set this one up now? All right, for this one, the pressure P1 would be 0.750 ATMs. Temperature 1 would be 128 plus 273. And then temperature 2 we're trying to find. Pressure is supposed to have increased to 1.5 ATM, so that would be your pressure 2, P2. Okay, so temperature 1 is 128 plus 273, which adds to 401K. Pressure 2 is 1.5, and temperature 2 we're trying to find. So you'd cross multiply 1.5 times the 401K would go here. Make sure you write your units down. That way you know which ones you're canceling. 401K. And this is ATMs. Divide both sides by 0.75 ATMs. This and this cancel, and this times this. ATMs cancel out. So 1.5. 1.5. How many?
802.
Okay, 802 Kelvin is what you get. The problem said to put the answer in Celsius, so you'd have to take away 273.
It's 529.
And then 529 K, 529 degrees Celsius would be the answer. Any questions? Are you all plugging in the numbers and then solving for the unknown, or are you rearranging the first equation?
I'm just calling what you're doing.
Is anyone rearranging the equation before plugging in the numbers? Who is? Oh, okay. And you're okay with that, right? Okay, which way, you can do whatever is best for you. So let's go back to the PowerPoint. All right, so let's go and now talk about vapor pressure. Vapor pressure is the pressure above a liquid at equilibrium in a closed container. So whenever you have liquid boiling in a container, or even if you don't have liquid, even if you have liquid that's not boiling, you're going to have some of the liquid is going to be in the vapor form, and the pressure of that liquid is called the vapor pressure. At the boiling point, vapor pressure becomes equal to external pressure. So when bubbles begin to form in a liquid, it's because the vapor pressure within the liquid becomes equal to the outside pressure, the external pressure, which would be 760 millimeters of mercury, remember, is the atmospheric pressure at sea level. So when the pressure inside the bubble is 760, which is equal to 1 atm, then bubbles begin to form. The boiling point of water depends on the vapor pressure, and it's lower at higher altitudes, because at higher altitudes, the outside pressure is lower, right? And on top of a mountain, we said the outside vapor pressure is not going to be 760 millimeters of mercury, but it's going to be like 500 or 600. So if the outside pressure was lower, then the pressure within the liquid is going to reach that outside pressure quicker, and it's going to start boiling quickly. So for example, when the outside pressure is 528 at the top of a mountain, then the liquid would look like it's boiling at 90. And it is actually boiling at 90. It's just not as hot as boiling water or boiling liquid. And what does that do to people that are trying to cook at higher elevations? Well, if the liquid is boiling, if they were trying to boil eggs, for example, the water appears to be boiling, but the temperature in the water is only 70 or 80 or 90. It's whatever you're trying to cook is really not going to cook. It's going to appear to be boiling but not cook, so you'd have to cook it for longer periods of time at higher elevations. An autoclave used to sterilize equipment attains a temperature higher than 100 degrees Celsius. An autoclave works like a pressure cooker, and you have to, there's high pressure within there, so water boils at a higher temperature, and that makes all the bacteria in your equipment die. Increasing the pressure increases the temperature at which boiling takes place in these equipments. This is just like the pressure cooker. Okay. So let's now go to